All right, so last class we went over simple interest, the I equals PRT formula. But there's also another method of calculating interest called compounding or compound interest. Okay, so again, last class was simple interest. Okay, so that means that the amount of bonus money you get, it is always the same. It's based on the original deposit, the principal. Okay, so it doesn't matter whether it's been 1 month since your deposit or 10 months or 100 months. Simple interest, you get the same payment every time. Okay, but then we also have what's called compound interest. Okay, so this means that your first interest payment is like normal. It's based on a percentage of the original, but your second interest payment, it's not just a percentage of the original, it's also a percentage of the first interest payment. And then your third interest payment, you get interest on the principal, the first interest payment, and the second interest payment. So every additional interest payment is a little bit more than the one before because you get interest on your interest. Okay, so the frequency of compounding, meaning how many times per year, there's different phrases we want to know. So when interest is compounded once per year, we call that annual compounding. Okay, so the word annual, like an annual event, is something like New Year's, something that happens once per year. We also have semi-annual compounding. Okay, so semi-annual means it happens twice per year. Quarterly, just like there's 4 quarters in a dollar, quarterly means 4 times per year. Okay, daily compounding. Okay, so you guys know that a year is based on Earth revolving around the sun. It's not exactly 365 days, it's a little bit more. So every fourth year about, we have an extra day called a leap day. But in general, we're just going to use 365 for daily compounding. Don't worry about leap years. Okay, so we've been going more and more times per year, right? From once per year, twice a year, 4 times a year, 365 days per year. You can also have continuous compounding. So you can recalculate the interest infinitely. So, more than like a million times per second. So it seems like that should be impossible. Like you would get infinite money if you're getting interest on the previous interest, but obviously that's not the case. Okay, and then we want to make sure we don't confuse this new term APY with APR, which we previously discussed. APY stands for annual percentage yield. Okay, so the word yield in this context is sort of like the output. So sometimes you hear like, oh, the farm yielded this many bushels of corn or whatever. So it's like the output, the product. Okay, so the APY describes what the interest rate would have been if it had been simple interest. Because again, when you compound, the interest is more because you get interest on your interest. So APY is basically just a different calculation that banks like to use to advertise because it's a bigger number. So it makes it sound better. Okay, so we'll talk about how to calculate the APY. Okay, but you've seen this formula before a couple times already, the compound interest formula. Okay, so I just give you a reminder of what each of the individual parts of the formula represents. Okay, so let's do some problems together. So you will want your scientific calculator for this. Again, if you need to check one out, I have a limited number that you just need to drop off your ID or something else. Yes. All right. So notice for this situation, it's compounded annually. Okay, so how much interest do you get in 1 year at an annual rate of 2%? Okay, so using the formula up here, the principal, the original amount is 1,000. Then you have parentheses 1 plus the fraction r over n. R, the interest rate, is 2%, but in decimal form. When you move the decimal point twice, you see that it's 0.02. Okay, and the number of times it's compounded per year. For part A, I said it's compounded annually. So annually means once per year. So n is 1. Okay, and then up in the exponent, we have n again. So n is still 1. And nt means n times t. T, the number of years, is also 1. Okay, so we can just type this into our calculator. Okay, so we got to be a little careful here because there's two questions being asked. One question is how much interest. The other question is what is the balance? So looking back at the formula, capital A represents the amount in the account, which is the balance. Okay, so this number right here is actually the answer to the second question. The new balance would be $1,020. Okay, the other question, how much interest was earned? Okay, the actual account is worth $1,020, but you already started with 1,000, right? So the interest is just the amount gained, the extra. Okay, so if you subtract, you see that you gained $20 of interest. Okay, so I told you that compounding is better for you when you are depositing money because you get interest on your interest. Okay, so part B, everything is going to stay the same except how often we compound. Okay, so we're still going to start with 1,000. It's still going to stay in there for 1 year. It's still going to be a 2% interest rate. The only difference is we're going to compound semi-annually instead of annually. Okay, so as we wrote above, semi-annually means that n, the number of times per year, is going to be 2. Okay, so again, you're still starting with $1,000. The interest rate is still 2%, but now n is 2 times per year. Okay, so typing this into your calculator, you'll get that the balance, capital A, is $1,020.10. Okay, so it is more than compounding annually, right? But not that much more. Okay, but yeah, the idea is that instead of you depositing the money, January 1st and getting the interest December 31st, you deposit the money in January, you get some interest halfway through the year, so like at the end of June. And then when you get paid again in December, you get interest on that first interest payment as well. That's where that extra 10 cents comes from. All right, so for these numbers, it's not that much, but if you deposit more money, or if the interest rate is higher, or if it's for more years, then it would make a more significant difference. Okay, and again, don't forget there's 2 questions per row. So we have the balance. Now, what is the interest? Again, you just take the final amount minus the starting amount. Okay, so in this case, you got $20.10 of interest. Okay, so I'm gonna ask you to go ahead and try out parts C and D. Okay, so if you have any questions, feel free to raise your hand. Okay, so just a quick note, in general, when you type this into your calculator, you need parentheses around the exponent. If you forgot to do that, for this problem, you actually would have gotten lucky because the times 1 is the same whether it's in the exponent or not. So you would have gotten, again, lucky, but if the number had been anything else, it would have made a difference. So again, you want to get in the habit of putting your exponent in parentheses when you use your calculator. Okay, so for part C, quarterly means n is 4. So the calculation for the balance would be 1,000 times parentheses 1 plus 0.02 over 4 to the power of 4 times 1. Okay, so that one comes out to $1,020.15. So that means that the interest is that minus the original 1,000. So still not a very big increase, right? Going from once per year to 4 times per year only gained you 15 cents. Okay, so let's make a huge jump, right? We're going to go from 4 times per year to 365 times per year, right? Over 90 times more often. So maybe that'll make a big difference. Okay, so again, we're going to use n is 365. We're not going to worry about leap years. We're just going to go with 365. Okay, so when we calculate this, we get $1,020.20. Okay, so the interest gained is $20.20. Okay, so you can see that the more often you compound, the more the interest. But with this particular set of numbers, the difference is not that big. Okay, so any questions on this section? Okay, let's go and turn to the back then. Okay, so we're still working with compound interest, but we're gonna do some different scenarios. Okay, Jose opens a savings account with $5,000 that pays 2% interest annually, compounded quarterly. Okay, so the principal, his starting amount is 5,000. The interest rate is 2%, so 0.02 again. Compounded quarterly, so n is 4. Okay, so first question, what's his ending balance after 5 years? Okay, so, sorry, we just fill in the numbers the same way we did on the previous page. Okay, so here it is going to make a difference how you type this into your calculator. Okay, so don't just wait for me to tell you the number. Go ahead and take a few seconds and try to type this in yourself, please, to make sure you can do it correctly. Okay, and you also want to make sure your answer makes logical sense, right? So when you start with $5,000, you're not going to end with like $20,000, right? You're not going to get 5 times your amount of money. So your answer should be reasonable. Okay, so if you type this in correctly, your answer, it goes on, the decimals go on forever, but since we're dealing with money, we'll round to the nearest penny. You should have gotten $5,524 and rounded to 48 cents. Okay, so again, if you got an answer that was in the like 25,000s, that means that you didn't put parentheses around your exponent. So again, if you're having any sort of trouble typing things into your calculator, let me know and I'll be happy to walk you through it. Okay, but then we have a second question for this situation. How long will it take for Jose's account to reach $6,000? Okay, so here I'm telling you the final balance, and the question is how long, meaning how much time. So the unknown is now t. Okay, so t is no longer 5 like it was over here. This time t is the unknown. Okay, so we know a equals p times parentheses 1 plus r over n times, or sorry, to the power of n times t. Okay, so this time the variable is not by itself, right? In the previous problem, the a was by itself on one side of the equal sign, so we just typed the whole right side in. But here we need to do some work to get the letter by itself. Okay, so the first thing I would do is get rid of this 5,000 that's in front of the parentheses. The 5,000 is touching the parentheses, so that means it's multiplying it. Okay, so the opposite of multiplying is dividing. Okay, so if we divide the right side of the equal sign by 5,000, we also need to divide the left side. Okay, we can go ahead and type this into our calculator. 6,000 divided by 5,000 is 1.2. Okay, so what we could do from here is this part has a variable, but the part in the parentheses is all just regular numbers. There's no letters in here. So let's go ahead and combine this highlighted part into a single number. Okay, so if you type 1 plus 0.02 divided by 4, okay, make sure you see here the 1 is not divided by the 4, only the decimal part. Okay, so this part should simplify to 1.005. Okay, and then don't forget, you still have the exponent. Okay, and the other side is unchanged. Okay. Okay, so the variable is still in the exponent, so we need to cancel out the 1.005 that it's an exponent of. Okay, so we learned this back in the 6.0e lesson, right? To undo an exponent, the inverse is a logarithm. Okay, so since we're trying to cancel out 1.005, we're going to do log base 1.005 of both sides. Okay, so log base, let me write it a little clearer down here. Okay, so log base 1.005 of the previous left side equals log base 1.005 of the previous right side. Okay, so again, you're allowed to do any operation as long as you do it to both sides of the equation. So here the operation is you took log base 1.005 of both the left and the right sides. Okay, so I'm going to continue over here because I'm out of room. Okay, so the left side cannot simplify. 1.2 is not a power of 1.005, so just leave that side alone for now. Okay, but the right side, right, the whole point was that we wanted to cancel out the 1.005, and doing log base 1.005 will cancel it out. Okay, so those parts cancel out, leaving the 4t behind. Okay, and then lastly, we want to get the t by itself. Right now, the 4 is in front of it, so we can divide both sides by 4. Okay, so now we want to get this into a decimal, right? Because what does this mean? Is this about 2 years, 3 years, 10 years, right? As it's currently written, we really have no idea how much this is. Okay, but if you look at your calculator, again, most of us don't have a log 1.005 button. We only have regular log, common log, and natural log. Okay, so we need to remember what we have what's called the change of base formula. We can take this and rewrite it as log of the argument. So regular log 1.2 divided by log of the base. So log 1.2 divided by log 1.005. Okay, so that's the top part, but we also still have the divide by 4 at the end. Okay, so this divided by 4 is still there. Okay, so let me show you how I would type this into my calculator. Okay, so I do common log, regular log of 1.2 and divide that by regular log of 1.005. Okay, so I'll just do that one first. And then I'll take that answer and do the divide by 4 to this. Okay, so you can see that this rounds to about 9.14. Okay, remember T is going to be in years. Yeah. Okay, so any questions on the way we set up and solved that equation? Okay, so then I'm going to ask everyone to go ahead and try both parts of the next scenario. Okay, so again, for daily, just use 365. Don't worry about leap years. Okay, so I'll be walking around. If you need any help getting started, feel free to let me know over it. So the first question, what's the ending balance? So here, you're starting with 1650, 1 plus R, which is 1%, so 0.01, over N, which is 365 because it's daily. times 365 times 3 for 3 years. Okay, so this one rounds to $1,700.25. Okay, so the next part was asking when would the account reach $2,000. Okay, so here should be the equation. Okay, so the unknown is the time, the number of years it'll take. So yeah, some of you had everything else, but you didn't put the variable. Again, you need a variable for your equation to have something to solve for. Okay, so the previous problem, the numbers worked out pretty nicely, right? 6,000 divided by 5,000 was exactly 1.2. Here, if we divide 2,000 by 1650, it doesn't work out as perfectly. This decimal goes on forever. Okay, so in general, more is better. The more decimal points you keep, the more accurate your answer. Or if you really want to be good, you can just keep it as a fraction. So in fraction form, 2,000 over 1650 reduces to 40 over 33. Okay, so I know most of you did decimal, and I did decimal above. Here I would probably do fraction because that's what keeps it exact. But since I know most of you did decimal, I'll show that way also. Okay, so this one would be, it's 1.21212121, so it repeats forever. So again, more is better. So I'll go 4 decimal places, I guess. Again, some of you I know stopped at 1.21, so your answer is going to be a little different just because of where we rounded. Okay, so same thing for the next part. If you try to simplify the number in the parentheses, you get a number that, again, the decimal goes to the edge of the screen. It starts with 1.000, but it won't work if you just keep it at 1. You need the numbers to be not 1. Okay, so I'm going to go until I get a number that's not 0. Okay, so it's 1.000027. Okay, so I'll round the 27 up to 3, I guess. Okay, and don't forget, this was just the highlighted parentheses. We still have the exponent attached to it. Okay, from here, we want to cancel out the 1.00003. So we do log of 1.0003 of both sides. The left side doesn't simplify, so you keep it as is. But the right side, again, the whole point was to cancel out that number, leaving just the 365t behind. Okay, and then now to get the t by itself, you divide both sides by 365. Okay, so for what you actually type into your calculator, in order to type in the numerator, you would rewrite it as common log of the argument divided by common log of the base. Okay, so you do that first, then you take that answer divided by 365. Okay, so when I type this into my calculator, I get approximately 17.57 years. Okay, so again, this is not a fully precise value because I rounded at so many steps. Right here, I rounded the fraction to this decimal. Then I took the parentheses and I rounded it even more. So it actually adds up to a really big difference. But yeah, that's the concept of how to get the variable t. Uh, so yeah, the actual value, if you did not round, if you kept it as a fraction, and if you kept this as the whole parentheses instead of rounding it, it actually is 19.24. Okay, so that's a huge difference, right? It's over a year and a half difference. And again, it all has to do with rounding. Okay, so yeah, in general, you don't want to round until the very end of the problem. Right here, I rounded at this step, I rounded at this step, and those two pieces of rounding made a big difference. Okay, but as long as I can see your work, I can see you did the right thing. That'll be the most important thing. If you just write down this answer out of nowhere, I won't be able to give you any points because I don't know you did it correctly, right? Because it's so far from the right answer. But if I can see that the only difference was the rounding, then that could show that you earned credit. Okay, so yeah, even though you'll have a calculator for the test, I still expect to see this sort of work so that I can follow your logic. Okay, so now let's get into the difference between APR and APY. So Sharon deposits $8,000 into a 1-year certificate of deposit at 2% APR compounded daily. The bank advertises that the APY is 2.02%. Okay, so yeah, these two numbers, right? APR 2% flat, APY 2.02%. Okay, so is the bank being honest with their numbers? Okay, so how we verify this is first we calculate the actual balance. Okay, so we're using the 2% right now. That's the actual value. We're not going to use this number because we don't know if it's true. Okay, so this part is just a regular compound interest problem. Sharon is starting with 8,000. The interest rate is again 0.02. Compounded daily is 365. So N is again 365, and it's a 1-year CD, so T is 1. Okay, so there's the variable is already by itself. We don't need to do anything to both sides. We just need to combine the right side into a single number. Okay, so using my calculator, I get $8,161 and rounds to 61 cents. Okay, so that's the balance in the account, but we also want to know how much interest was gained. Okay, so she started with 8,000 already. Okay, so the amount of interest gained was $161.61. Okay, so now we're going to compare that to the claimed APY of 2.02%. Okay, so APY uses the simple interest formulas. Okay, so this is the formula from last class, I equals PRT. Okay, so we're trying to confirm that the amount of interest is correct. So I is our unknown. Okay, she's still starting with $8,000. Their claim is that the interest rate is 2.02%, which in decimal form would be 0.0202. And the time is still 1 year. Okay, so again, the unknown is already by itself, which is great. We just need to type the right side into our calculator. Okay, so 8,000 times 0.0202 times 1. The interest earned is 100. Oh, sorry, I mistyped it. $161.6 or 0.60. Okay, so comparing the two numbers, okay, yeah, they're a penny off. It's just a rounding thing. So yeah, I think we can say that the bank was accurate. Okay, so 2% compounded daily is the same thing as 2.02% in simple interest. Okay, so again, the bank will say 2.02% in their commercials and advertisements because it's a bigger number than 2%. Okay. Okay, so again, APR, that's compounded daily. We use the compound interest formula, but APY is simple interest, so you use simple interest formula. Okay, so we have one last type of compounding interest, and this is continuously compounded. Okay, so continuously means it never stops. Okay, so again, you can compound more than 1,000,000 times per second. Again, it seems like that should be infinite money because we talked about you're getting interest on your interest. But as we saw on the bottom of that front page, when we jumped from once per year to 365 times a year, that only increased by 20 cents. So the amount you gain is going up by so little that it eventually flattens out, it levels off. Okay, but then the formula that we use for continuously compounded looks a little different. Some parts are the same, right? We've got the capital P in front, we've got the RT in the exponent, but the parentheses has turned into the number E. Again, lowercase e is not a variable. It's Euler's number. It's about 2.7, but you don't need to memorize that. Okay, so Marie wants to have a continuously compounded savings account. She deposits $16.50 at interest rate of 1%. Okay, so let's go ahead and substitute into the formula. We want to find the balance. So A is the unknown. She's starting with $16.50, so that's the principal. Again, E is not a variable, so you don't replace it. You just keep it as E. Interest rate of 1% is 0.01, and times T, the time in years, it's been 3 years. Okay, so this is what we type into our calculator. Okay, so you do have an E button in your calculator. So first I type in the coefficient 1650. Okay, and then right above the ln button, hopefully you can see that there's a e to the power of x. So I do second that button. Okay, and you notice it already creates the exponent for me because the way e works, it pretty much always has an exponent. Okay, so it's e to the power of 0.01 times 3. Okay, so $1,700 and rounds to 25 cents. Okay, so that number may sound a little familiar. If you look up above, that was the amount of money that she got from compounding daily. So in this case, there's not even a penny difference between compounding daily and compounding continuously. Okay, so for larger numbers, there would be a difference, but it's not that much. Okay, and then now when will this account reach $2,000? Okay, so that means we want the balance to be 2,000, but the unknown is the time, how many years? Okay, so 2,000 equals 1650 times e to the power of RT. Okay, so this time let's not round anything. Let's keep our numbers exact. Okay, so first, sorry, I made a mistake. The unknown again is the time. It's not 3 years, it's an unknown number of years. So it should have been t. Okay, so first we want to get rid of this 1650. The 1650 is in front of the e, so it's multiplying. So divide by 1650. Okay, so as we saw above, if you divide 2,000 by 1650, it doesn't work out nicely. It's a long repeating decimal. Okay, so what we can do instead is to just keep it as a fraction. Okay, so now, in case you weren't aware, you should have a fraction button. For me, it looks sort of like this mixed number symbol. Okay, so instead of a divide by sign, I can push that button. So now it means the numerator is 2,000 and the denominator is 1650. Okay, so if I push equals now, it reduces the fraction for me. Okay, so it's telling me that this fraction is equal to the mixed number 1 whole and 7/33. Okay, now if you want it to be an improper fraction, the second version of that button, you see it goes from mixed number to a common fraction. Okay, so I can take this and then do second that button to switch it from mixed number to improper fraction. Okay, so the fraction simplifies to 40/33. Okay, so again, on my calculator, I just showed you that this reduces to 40/33. Okay, my goal is to get the t by itself, so I need to cancel out the e that it's currently a part of. Up above, to cancel out the 1.00003, I did log of 1.00003. Here, to cancel out the e, I would do log base e, but remember that log base e is called natural log, ln. Okay, so we do the natural log of both sides. Okay, the left side does not simplify, just keep it as is. But the right side, again, the whole point is that natural log is log base e, so it cancels out the other e. Okay, leaving just the exponent of 0.01t behind. Okay, and then lastly, we need to get rid of this 0.01 that's in front of the t, multiplying it. So we divide both sides by 0.01. Okay, so in the end, we get natural log of the fraction 40/33, all divided by 0.01 will equal t. Okay, so I'm going to go and type this into my calculator. Again, you have a ln button, natural log. So natural log of the fraction 40/33, close parentheses, right? The whole fraction is in the natural log, but then the divided by 0.01 is outside the natural log. Okay, so about 19.24 years. Okay, so one more similar set of problems below. Go ahead and take a few minutes and see if you can solve this last section. The first one, what's the balance after 5 years? Sorry, 1 second. Okay, so $1,000 principal, interest rate is 2.3%, which would be 0.023 or 0.023. And the time is given as 5 years. Okay, so again, here the variable is already by itself. So you just type the whole right side into your calculator to get $1,121.87. Okay, then over here, when will your account reach 1,500? So that's the desired balance. Okay, you start by getting rid of the coefficient. And this one does divide nicely. So you could keep it as the fraction 3/2, or it just equals exactly 1.5, so you can do decimal also. To cancel out the base of e, we do natural log of both sides, which remember means log base e. Oh, sorry. Okay, this side doesn't simplify, so you just keep it. But this side, the whole point was to cancel out. Okay, and then lastly, to get rid of the 0.023, divide both sides by 0.023. Okay, so if you have questions on any of that, feel free to raise your hand as I walk around.